Before automation touches controller inventory, make the request explain its target, action, credentials, and response. A network engineer needs manage device inventory before a change window closes. The tool sends a request, but the controller refuses it. Instead of guessing, solve one decision at a time. What resource is wanted? What action is intended? And what authorization proves the tool may ask? Those decisions turn REST vocabulary into a practical workflow. An application programming interface, or API, is the agreed doorway into an application's data and services. Without it, every pair of applications needs a custom integration. Add a new tool, and the tangle grows. With a uniform API, several callers can request appd's data without knowing its internal code. Caller sends a request. The API interprets it and returns a response. In network automation, REST APIs commonly use HTTP for that conversation. HTTP uses a client-server exchange. The client sends a request to a resource. The server processes it and sends a response. A URI identifies the target resource. It does not tell the server what to do. The HTTP method supplies that decision. Headers add context, including authorization when required, and a request body is optional. The response carries a status code and may carry data, often JSON. Think resource first, then operation. CRUD is the shortcut. Create, read, update, delete. Common mappings are post to create, get to read, put to replace, patch to modify, and delete to remove. PUT replacement and patch modification are a useful distinction, but they are conventions, not a promise that every API behaves identically. Documentation defines the exact semantics. For example, an automation tool can ask a controller to create a new ACL rule. The resource is the rule collection. Post expresses the common create action. If processing succeeds and a new rule exists, 201 created is a useful, expected result. The same resource still needs a different method. When the tool wants to read it, modify one field, replace the full representation, or remove it. Keep URI and method separate. The URI says where, while the method says what. Next, use the response as evidence. Start with its first digit. 1XX is informational, 2XX successful, 3XX redirection, 4XX a client error, and 5XX a server error. Know the landmarks. 200 OK means success. 201 created, confirms a new resource. 403 forbidden usually signals insufficient authorization. 404 not found points to the target. 500 internal server error means the server could not complete an apparently valid request. A 4XX response is not proof that the server failed. REST makes these exchanges predictable through 6 constraints: uniform interface, client-server, stateless, cacheable or non-cacheable, layered system, and optional code on demand. At CCNA depth, focus on their consequences. Client and server can evolve independently behind the interface. Stateless means the server does not use prior client requests to decide a new response. HTTP may ride on TCP, but TCP state does not make REST stateful at the application layer. That statelessness explains a security rule. Every protected request carries the authentication information it needs. It also explains why cacheability is deliberate. A frequently accessed web page can be marked cacheable and reused. A real-time account balance should be non-cacheable. Reuse can show stale data and store sensitive information inappropriately. HTTPS protects passwords, keys, and tokens while they travel. It does not decide whether a resource is safe to cache. Choose authentication by what the credential represents. Basic authentication sends a username and password in a request header, so HTTPS is essential. Bearer authentication sends an access token, usually limited in lifetime. An API key identifies a client application and commonly remains valid until revoked. An API key is not a user token. OAuth 2.0 is different again. It is a delegation framework. A user can authorize a third-party client for a limited scope without handing that client the user's password. In a typical OAuth flow, the client asks the resource owner for authorization. The resource owner grants it. The client exchanges that authorization grant with the authorization server for an access token. Then, the client presents the token to the resource server, which enforces its scope before returning the protected resource. The token grants only the approved access, and it still needs HTTPS in transit. Now resolve the opening problem with Catalyst Center inventory. First, the automation tool sends a POST request using basic authentication to obtain an access token. Keep credentials and the returned token redacted. A 200 OK response confirms the token request succeeded. Only then does the tool send a GET request for the inventory resource, carrying the documented X-Auth-Token header. The controller validates the header and returns inventory data as JSON. The lesson is the order, not a copied endpoint or secret. POST obtains temporary authorization. 200 OK confirms it. GET reads the protected inventory. JSON carries the result. If the call fails, troubleshoot in order. Resource URI, HTTP method, headers, authentication, status category, then response body. For any unfamiliar REST scenario, ask 5 questions. Which resource URI is the target? Which HTTP method matches the intended action? What authentication must this request carry? Which status category describes the outcome? What does JSON represent in the response? Then explain why the exchange behaves that way. REST is stateless, and a resource must be deliberately cacheable or non-cacheable. That is how a blocked inventory lookup becomes a repeatable decision process. APIs provide the uniform doorway. HTTP carries request and response. REST keeps the exchange predictable. Authentication protects access. And the response tells the automation tool what to fix next.